Welcome to the Crazy Hat Chemist. So another video here on equilibrium. So let's get moving. Bam! So today we are talking about equilibrium calculation number 4. Let me read the question to you. Dinitrogen tetroxide, NTO, a colorless rocket propellant, can be converted to nitrogen dioxide, a reddish-brown gas, with the addition of heat in the following equilibrium reaction below. You're going to see that in just a second. Nitrogen dioxide gas accounts for much of the color of the reddish-brown smog in industrialized cities at sunsets. If the initial concentration of dinitrogen tetroxide is 0.50 molar, what are the equilibrium concentrations of all species? Given that we have the Keq is equal to 5.9 times 10 to the negative 3 at 298 Kelvin. That's 25 degrees Celsius. That's about room temperature. Now, one of the questions is this reactant or product favored as it is with that Keq? Since that exponent is negative, it's a negative 3, that means that this reaction is reactant favored, as is written at 25 degrees Celsius. That's 298 Kelvin. So here's the equation. It said that there is a heat term on the reactant side. That lets you know that this is an endothermic reaction. Okay, so if you were to decrease the heat, the reaction will shift towards the reactants, and then you get more N2O4. Okay, if you increase the heat, then the reaction will shift to the right towards the products, and you'll get more NO2. Okay, so the N2O4 is colorless. So on the top of the slide here, I have equilibrium calculation number 4. On the left-hand side, you should see that there's a tube there filled up with these gases. And as you cool down the tube, it goes from a reddish-brown color that's on the tube on the right, which is at room temperature, all the way to that yellowish gas that is more dinitrogen tetroxide, okay, which is going towards the colorless region. The tube on the far right-hand side is the product of NO2. That's nitrogen dioxide gas, and that's that reddish-brown gas. That's what we see these beautiful sunsets all about. All right, so we're going to have to do an ice table on this one as well. Remember? Ice, ice, baby. Boom, ba-da-ding-ding-ding-ding. Ding-ding-ding-ding-ding-ding. Okay, here we go. Initial, change, and equilibrium. Okay, and we do have a value for the initial amount of the dinitrogen tetroxide. That is 0.50 molar, and that's going to go right there. Now, what is the initial concentration of the product? What is always the initial concentration of the product? And that is going to be a 0. Now, there's going to be a shift. That is, I have some of the reactant and nothing on the product side, so it's going to have to shift towards the products. That means that the reactant is going to decrease. The products are going to increase. As the reactants decrease, that's where the negative sign is coming from. As the product increases, that's where the positive sign is coming from. Now, I'm looking at the stoichiometric coefficients in front of the dinitrogen tetroxide, which is a 1, and the nitrogen dioxide, which is a 2. And I'm going to be using those stoichiometric coefficients. So it's a minus 1x for the dinitrogen tetroxide because it's on the reactant side. It's a minus, and it's a stoichiometric coefficient of a 1 in front of the dinitrogen tetroxide. That's why it's a 1x. Now, on the nitrogen dioxide, which is the product, it's going to be a positive because it's a positive product, and you're making more product. And it's a 2x because the stoichiometric coefficient in front of the nitrogen dioxide is a 2. Now I have my initial, my change. I'm going to add up the two columns. So I'm going to add up the 0.50 minus the x, and I get 0.50 minus x. And I'm going to add the 0 plus the 2x, and I'm going to get 2x. And what I'm interested in is truly what's in here at the equilibrium state. So now what I need to do is write the Keq expression. That is, all Keq expressions are the same. That is products over reactants with the stoichiometric coefficients as exponents. So let's do that right here. I only have one product, one reactant, so that shouldn't be a problem. So here I got my Keq expression. That's NO2 to the second power, that's with an exponent of 2, divided by N2O4 to the first power. I'm going to plug in these values that I got right in there at equilibrium and my equilibrium constant. Bam! Right there. Okay, now I need to solve this mathematically. Okay, so here is a little bit of solving mathematically. Now remember, it's 2x quantity squared, so that 2x quantity squared is going to be a 4x squared. Hopefully that works out well for you. So, and I'm going to get rid of that denominator term and move it over to the numerator of the other side there. And that's what I've got right there. So now I'm going to distribute the 5.9 times 10 to the negative 3 with the 0.5 and with the negative x, and I'm going to take care of that 2x quantity squared and make that into a 4x squared. So that's what I've done there, is I've distributed that term outside the parentheses, and I've got that 4x squared term. Now what I'm going to do is rearrange this so that it looks pretty mathematically. And I've put the 4x squared in the front. So I got my x squared term first, then I have my x term, then I have my non-x term, and this all equals 0. Now this should be starting to look familiar to you, and I put it in this form so that it does look familiar to you. And this is that familiar form. And what is that? That is a quadratic equation. Okay, so where is the A? This 4 is the A. What is the B? It's 5.9 times 10 to the negative 3 is the B. What is the C? The C is a negative 2.95 times 10 to the negative 3. What is the quadratic equation in solving for what I'm looking for, which is that x, of course, and here it is. So it's negative b plus or minus square root b squared minus 4ac all over 2a. At the end of this video, I'm going to show you a really simple way to remember that format right there. So don't end the video too soon, okay? You're going to miss the hat and a simple way to remember this equation. All right, so I've plugged it into the quadratic equation. I'm solving for x. I'm going to get two numbers. One of them is going to be using that plus sign in front of the radical, and the other one is going to use the negative sign in front of the radical. Hopefully you got all those numbers correct. I've just plugged it in, A, B, and C, as is appropriate, into the quadratic equation. Now, I'm going to get two values here. One of them is going to be 0.026. The other one is going to be negative 0.028. Now, mathematically, both of those numeric values are equally valid. However, since we are in a chemistry class, then we need to be thinking about chemistry. And since the negative value is a negative value and we cannot have negative concentrations, that would not be a good thing. We're going to delete the negative value. So I'm going to get rid of the negative value and I'm going to be using just the positive value. Okay? So now what we're going to do is we're going to plug this in to the equilibrium numbers that we have with the x term. So we're going to substitute this x in for the N2O4 and the NO2. So I had a 0.50 minus x, so it's going to be 0.50 minus 0.026, and then I'm going to say 2 times x, which would be 2 times 0.026. Okay, so here is both of those plugged in there as is appropriate. So my dinitrogen tetroxide concentration at equilibrium is going to be 0.47 molar. And my nitrogen dioxide concentration at equilibrium is going to be 0.052 molar. Again, I highly recommend that you plug these numbers back into the Keq expression, and you should be getting back out the Keq value. Again, there is some rounding issues, so don't worry about that. Okay, but you should be very close, in other words. Okay, now, I've got the way to remember the quadratic equation. And I'm going to include my hat on this just because, wow, it's getting a little bit chilly in here, and I need a hat. So, thank you very much for the hat. One of my students gave this to me. I believe it was Sean. So, remembering the quadratic equation, here we go. This is the quadratic equation, which is minus b plus or minus square root b squared minus 4ac all over 2a. So how do you remember this? Well, here's the story. There was once a negative boy. See that negative boy right there? Who couldn't decide, that's why it's plus or minus, who couldn't decide, whether he wanted to go to a radical party. Woo! Okay, the boy remained square, too bad for him, and missed the chance to meet 4 awesome cheerleaders. The party got over at 2 a.m. So that's the way to remember the quadratic equation. Okay, I don't remember where I heard that from, but I heard that from someone a long time ago. Give me a thumbs up if you like that video, subscribe to my YouTube channel, and check out my website. I got all my videos on there and a bunch of worksheets. Okay, thank you very much. Have a great day. See you next time. Bye for now.